Microsoft has taken a significant leap forward with its innovative large action model, designed to move beyond simple text generation. This advanced AI tech allows for task execution directly within the Windows environment, bringing the gap between language models that generate content and systems capable of interacting with software. LAM was developed to interpret user instructions, create actionable solutions, and execute these steps within applications like Word, Excel, and PowerPoint. It's a transformative approach that could redefine how users interact with their operating systems. Training methodologies, building execution capability. To make LAM effective, Microsoft combined various advanced training techniques, including supervised fine-tuning, imitation learning, and reinforced learning. These approaches were used in tandem to equip the model with robust planning and execution skills in dynamic environments. The training process required a massive data set that included task descriptions and real-world action sequences. Sources ranged from official software documentation and WikiHow articles to Bing search queries. To turn this unstructured data into actionable training pairs, Microsoft used GPT-4 to generate structured task-action combinations. The dataset covered a broad spectrum of scenarios, from simple instructions like changing text fonts in Word to more intricate tasks involving customized styles, form filling, and complex formatting. To enhance task complexity, the team employed a technique called data evolution, where GPT-4 would enrich basic instructions by introducing additional conditions or steps. This iterative process resulted in a database containing over 76,000 task plan pairs, which laid the groundwork for LAM's capabilities. Converting instructions to actions. Training LAM to translate textual instructions into executable actions was a complex undertaking. Microsoft took an additional step by developing task action data, where plans were paired with corresponding interactions, such as selecting or clicking buttons. This required not only mapping the instructions but also enabling LAM to understand the graphical user interface and its functionalities. For example, clicking on the text highlight color button in Word required linking the instruction to a precise function call. A multi-phase training pipeline. Microsoft's journey to perfecting LAM involved a structured four-phase training pipeline. Phase 1. Developing planning capabilities. The initial phase involved training a base model named Mistral 7B to draft coherent task plans. This version, referred to as LAM 1, could outline steps for basic tasks like inserting images or selecting fonts in Word. However, it lacked the ability to perform the actual interactions required for task execution. Phase 2. Incorporating action steps. The move beyond planning, the team trained LAM 1 using 2,192 examples annotated by GPT-4. These examples detailed action sequences required for tasks within Word interface. This effort gave rise to LAM 2, which could generate action steps and simulate user actions like selecting menu items or typing inputs. Phase 3. Self-discovery of solutions. LAM 2 was further tested with tasks GPT-4 had previously failed by attempting and succeeding in solving some of these challenges. LAM 2 also contributed an additional 496 successful action sequences to the dataset. This iterative learning process produced LAM 3, which had enhanced problem-solving capabilities. Phase 4. Reinforcement learning for optimization. In the final phase, a reward model was introduced to fine-tuning decision-making. The system rewarded successful actions with positive scores and penalized errors, optimizing the model through reinforcement learning. The result was LAM 4, a robust model capable of systematically learning from both successes and failures. Performance evaluation, offline and online testing. LAM's performance was evaluated through rigorous offline and online testing. Offline tests included 435 tasks in Microsoft Word, ranging from opening a blank document to advanced formatting tasks, such as creating tables or extracting data from files. Metrics included success rates, step-by-step accuracy, and the model's ability to identify the correct interface elements. LAM 1 achieved a 35.6 success rate. LAM 2, enriched with GPT-4's examples, saw success at 76.8. LAM 3, bolstered by self-discovered solutions, reached 79%. LAM 4 reached 81%. Comparisons with GPT-4 revealed LAM's superior performance in task execution. GPT-4 in text-only mode achieved 67.2. A smaller GPT-4 variant managed 62.3. Even GPT-4 with visual input reached only 75.5, lagging behind LAM 4. In live Windows environments, LAM completed tasks with a 71% success rate. Tasks were executed on a virtual machine running Microsoft Word, with the model relying solely on text input. In the setting, LAM took about 30 to 42 seconds per task, completing them in an average of 5.62 steps. GPT-4 with only text input managed 63% success, but required 86.42 seconds on average. GPT-4 with visual input achieved a higher success rate, 75.5, but was slower, taking 96.48 seconds on average. Integration into Windows, the UFO agent. To further enhance LAM's functionality, Microsoft integrated it into a Windows-based agent called UFO. This agent processed GUI elements on screen, determined their names, coordinates, and purposes. UFO then uses LAM to decide which controls to interact with and how to execute user instruction. Once the plan is formulated, UFO performs the necessary actions, such as clicking buttons or typing text while tracking progress. This integration allows LAM to act as a real-time assistant, executing tasks across different applications. For instance, users could interact with LAM to copy data from Excel, navigating to a website, and paste that data into an online form. Unlike models that merely generate text-based instructions, LAM performs the steps autonomously. Broader applications and challenges. While LAM's ability to execute tasks autonomously is a significant breakthrough, it also introduces potential safety concerns. If the AI misinterprets a command or veers off course, the consequences could be substantial. To address this, Microsoft has implemented strict error-checking mechanisms and may require user verification for critical steps. Expanding LAM to other operating systems such as macOS or mobile platforms present additional challenges. Each environment requires a unique dataset of labeled examples for the model to learn from, which can be a time-consuming process. Techniques like transfer learning and multitasking learning may expedite this process, but they remain areas of ongoing research. Future prospects beyond Office applications. Microsoft envisions LAM as a step forward toward broader general AI capabilities. The technology could potentially extend to controlling other desktop programs, robotic platforms, or even complex systems in domains like finance and healthcare. By moving beyond text-based responses to actionable execution, LAM represents a paradigm shift in AI-driven automation. However, this progress is not without ethical considerations. Issues such as accountability, bias, and safety remain passing concerns, particularly when AI systems are tasked with operating in high-stakes environments. Despite these challenges, Microsoft's research demonstrates that domain-specific training can yield models that outperform general-purpose systems in targeted applications. Conclusion: pioneering a new era of AI interaction. Microsoft's large action model is a groundbreaking development that signals the beginning of a new era in AI tech. By enabling AI to execute tasks directly within applications, LAM goes beyond traditional language models, offering users a more dynamic and interactive experience. While challenges remain, the potential of LAM to revolutionize workflows across industries is undeniable. This milestone highlights Microsoft's commitment to pushing the boundaries of AI innovation. Whether it's automating complex workflows or integrating seamlessly into everyday applications, LAM sets the stage for a future where AI doesn't just assist, it acts. The question now is whether the pace of AI progress is too rapid or simply a natural evolution of technology. Either way, LAM exemplifies the transformative potential of AI in reshaping how we interact with digital environments.